Okay. So one thing I did want to say on the grading and whatnot is I'm still one homework behind, but I'm going to try and knock out homework 3.1 maybe today, so that 3.1 and maybe 3.2 I can get caught up this week. I'll say this: your homework that's assigned today, that's due Wednesday, of the 4 trust assignments, is probably the shortest because there's really just one joint you need to solve for. And that'll be sort of the focus of the discussion today. But one thing I did want to say that I've sort of noticed a little bit on the homework assignments, and it's really more of a piece of advice for you, not only to score better on homeworks and exams, but also make the work go a little bit faster. And it seems counterintuitive, but one thing I would do is spend a little bit of time on this part. And by this part, I mean the free body diagram, okay? I'm noticing that there's not a lot of you, but some of you are sort of like rushing through this part, and I'm imagining what's happening is because the free body diagram isn't neat, you get to the point where you're summing moments and you're sort of like staring at it because the answers aren't coming out the way you want. If you take a little bit of time and accurately draw out the loads and the dimensions and the reactions and all that, and put a little care into this, I do believe it makes the moment summation and the section cuts go not only easier but faster. Okay, so I know it seems a little counterintuitive to spend a lot of time drawing a picture, but I think at the end of the day, the homeworks will result in a net decrease in time and an increase in score if you pay careful attention to your free body diagram. I was grading homework 2.4, and I sort of noticed a correlation between the students who were making mistakes, and then you look at the free body diagram, and it's sort of dialed in a little bit. So take the time, construct it carefully. Chances are there'll be less mistakes. And I have this solution posted on Blackboard for anybody to review. And I mention that because, I mean, this is a very graphical class. You're drawing a lot of pictures in relation to the math. So I think that's kind of important. Okay. Did everybody get the QR code? Okay. So I've sort of theoretically discussed everything that there is to discuss with the method of joints. So that sort of begs the question, well, if that's the case, what are you going to talk about today? I have 2 sort of tangentially related topics today regarding the method of joints. And I think they are worth discussing in some detail because they can happen in a real-world analysis. And this is just sort of extra, I guess today's theme is extra tools in the toolkit for analyzing trusses. So we're going to look at 2 different things today. The first thing we're going to look at is solving a 2x2 system for equations of joints, or 2x2 system of equations for joints analysis, which is why I wanted everybody to bring a scientific calculator today. And then also the identification of zero-force members. Zero-force members are going to pop up quite a bit, not just in practice, but later on when we do virtual work. And so you do need to be aware of handling that. I'm going to skip past the method of joints assumptions because I think we understand that at this point. I want to go back to maybe high school. Maybe this is something you covered in Math 127 or Math 132. Maybe it showed up in calculus, I'm not sure. But I know that everybody in here has had this type of math problem before. Okay? So this is a class of problems revolved around the solution of simultaneous equations. Okay? So the idea behind a simultaneous equation solution is, let's say you're given 2 equations. So we'll say x plus 2y equals 3 and 2x plus 3y equals 4. And the goal is to find the magical set of numbers x and y that satisfy both equations. Okay? And I'll go ahead and tell you the answer. The answer is this is true when x is -1 and y is 2. Okay? And if you don't believe me, what is -1 plus 2 times 2? It's 3. What is -2 plus 6? It's 4, right? That is the only pair of values that satisfies both equations. If you change any one of those values, either the x value or the y value, you won't satisfy both of them, okay? Essentially, this and this are just rewritten equations. equations of a line, okay? And -1, 2 is the point where those lines intersect. And two lines only intersect in one place, okay? Everybody with me so far? There is an entire school of math dedicated to this field, and that school of math is called linear algebra. So if you ever take a course in linear algebra, this is what you do. It's solve the solution of simultaneous equations. Why? Because it shows up in science and engineering all the time, okay? Now, there are oodles and oodles of methods to solve simultaneous equations, and again, there's a whole class of math devoted to that. I'm only going to discuss 3 in here. Let's just go back to either high school or Math 127, 132. So let's start off with substitution. Okay, so how does substitution work? Okay, so we take one of the equations and we isolate one of the variables. Okay, so I'll take the first one and I'll solve for x. So if x plus 2y equals 3, that means x equals 3 minus 2y. So if I know that x equals this pile of junk, what I'll do is in the second equation, instead of x, I will substitute that pile of junk. So instead of 2x plus 3y equals 4, I say 2 times all of this. So I substitute into the second equation the knowledge I got from the first equation. So do a little bit algebra, y equals 2, okay? Take that value of y equals 2, I can then plug that into either one of the other expressions, doesn't really matter, and I get x equals minus 1. Is this something you all have seen before? I'm hoping everybody's done this before, okay? Okay, that's method number 1. Here's method number 2, which is elimination. So elimination is, and this is more about how computers do linear equation solution, is they take the equations and they ask themselves, and I use the term magic even though it's not really magic, but they take the, let's say one of the equations, and I'm going to multiply it by this magic number of minus 2. So instead of x plus 2y equals 3, I'll get minus 2x minus 4y equals minus 6, okay? Now, why did I do that? Because if I take equation 1, that modified equation 1, and just add the whole thing term by term up with equation 2, the x terms cancel. So I was looking forward into the future, and I'm saying, well, if I multiply this value by -2, the -2x and the positive 2x cancel, or they are eliminated, and then I ultimately generate y equals 2. I can take that y equals 2 value, back substitute it, get x equals minus 1. Okay? Has everybody seen that before? I'm hoping everybody's seen that. To be honest, most computational engines like the software program that shall not be named, known as MATLAB, that's what MATLAB primarily does when it solves for simultaneous equations. Okay, except if it gets super, super big. Again, take linear algebra and talk all about it. Okay, now what we're going to do in here, and there's a reason why we're employing matrix algebra, because we're going to talk about matrix analysis later in the semester, is we're going to use matrix algebra because it's a little bit more standardized. So the way matrix algebra works is we take the set of equations and we rewrite them in matrix form. And so whenever you write a set of equations in matrix form, you're going to have a square matrix of coefficients. And so this coefficient matrix is 1, 2, 2, 3. Where am I getting that? 1, 2, 2, 3. Right? So I'm just writing those coefficients out in a big old table. I have a column vector. So if you ever have a matrix that only has one column or one row, we call that a vector. Okay? So that has x and y. And then this over here has 3 and 4, the 3 and 4. Okay? Now, the reason why we like to write it in this way is because it provides a very simple, standardized means of solving this system. So the idea is that if I have, we'll call this commonly what this is called in linear algebra is AX equals B. And if that's AX equals B, then X is just A inverse times B. And the reason why I'm introducing it this way is because this is how computers love to solve matrices. And why that's important is because this is how computers solve structural analysis problems. Okay, so we're going to see this a little bit later this semester, which is why I'm trying to get you familiar with matrix notation now. Okay. Now, this is fine for 2x2 systems. It's fine even really for 3 by 3. The downside to this method is that it's really laborious to do by hand, okay? So if you had a 4 by 4 system or a 5 by 5 system, computing a matrix inverse by hand is kind of a nonsense exercise. But computers love to do it, okay? This computer that's displaying this PowerPoint that we're watching, computers can really only do two things, and that's count and add. They just do it really fast, okay? And that's all this is counting and adding, and computers love to do that. Okay. Now, the reason why I wanted you to bring your Casio FX115ES Plus or similar scientific calculator is because these calculators have routines built into them that will do matrix solution for you, okay? This is a very common feature for most scientific and graphing calculators. If you go to Blackboard, okay, what you'll see on Blackboard is, so today in class, I'm going to assume everybody has a Casio. If you don't have a Casio, if you have some other brand, a TI or what have you, I posted a playlist on Blackboard that walks you through how to do simultaneous equation solutions if you have another calculator. And don't worry, we're going to do this together. This example that we'll do, I'll even write the modes and whatnot. But what you're going to do is, just to give you the high level, whenever you're generally using your Casio, you're in mode 1. So if you hit mode and 1, that's the computational mode. That's just how you do 2 plus 3 or the sine of 40 degrees or what have you. But if you go to mode 5 is equation solution. And so what we're going to do today is we're going to do mode 5 and we're going to do option 1. And so basically what you would do is just enter in the table of values, the coefficient at the end, just press enter, it gives you X and Y. Really, really straightforward enterprise. Okay? Sound good? Let's do an example. Okay? So I have here a method of joints problem that I want to solve together. And this is an interesting little, what I call it, this is a scissor truss. And I've given you the reactions because, again, I think the reactions are a fairly straightforward enterprise to compute. But here's the issue, okay? Let's think about this strategically. Could I solve joint B right now? Joint B. How many unknowns are going through joint B? 3. And the loads are not symmetric. Okay. Now we're going to talk about symmetry here in a sec, so I guess we could maybe try and attempt joint C, but I want to see about solving joint A. Okay. And there's going to be an issue when we solve joint A, because if I look at joint A, I've got a member going like that, and a member going like that. I've got a load like this, a load like that. But the problem is they're both diagonals, right? So I'm going to have a vertical and a horizontal unknown, a vertical and a horizontal unknown. So the problem is if I sum forces in the x direction, I have 2 unknowns. If I sum forces in the y direction, I have 2 unknowns. Okay, so that is a little bit challenging. So does that mean that we cannot analyze joint A? No, we can analyze joint A if we break out some matrix algebra. So again, the whole point of this problem is to do just that. Okay. Now I'm going to walk you through it a little bit, okay, and show you how we'll handle this. All right. Okay. So the first thing I want to point out is that member AB is on a 1-to-1 slope ratio, and member AC is on a 1-to-2 slope ratio. Okay. So we're going to use that to look at each of these components. And before we start getting into the actual truss analysis, let's take a look at the slope ratios. Okay, so member AB is at a 1-to-1, member AC is at a 1-to-2. So, all right. Okay, so let's take a look at this. So So if this is 1 and 1, what does that make that? The square root of 2? Is that right? And if we have this right here, this is AC. This is 2 and 1. So that makes that the root of 5. Is that a fair statement? Right, so this is 1 and 1 squared root of 2. This is over 2 up 1. So 2 squared plus 1 squared equals 5. So that's the square root of 5. Is that okay? All right. Now, probably the trickiest part with these problems is what I'm about to do right here. Okay. Now, up until now, when we do a method of joints analysis, what we're doing is we solve for, let's say, the x component, and then we use the slope ratio to find the y component, or vice versa. We solve for the y component, use the slope ratio to find the x component. We're doing something a little different here. What I want to know is ABX equals something times AB, and ABY equals something times AB. Same thing over here. ACX equals something times AC. ACY equals something times AC. In other words, there's a coefficient in front of each of these, and I want to see if I can figure out what these are. So instead of relating x and y to each other, I'm relating independently x and y to the hypotenuse. So if I'm relating it to the hypotenuse, for both of these, I'm going to have a denominator of root 5. Okay? And as for the numerator, now I can use the 2 and 1. So we'll call this 2 and call this 1. Does that make sense? So this is a little different. We didn't do this before. Okay? We're doing it solely because we're doing a 2 by 2 solution here. So what fraction goes over here, if that's the case? What's the fraction here?
Would that both be 1 over root 2?
The 1 over root 2, okay? And I know that somebody's going to say, well, wait a minute, aren't you not supposed to have a radical in the denominator because isn't that an improper fraction? Yeah, I don't care. I really don't. It doesn't bother me. I'm sure there's a math professor out there who said, excuse me? Okay. All right, so here I'll drag this down a little bit too, so it's a little bit separated. Okay. All right, does that make sense? That the idea that the y component is a fraction of AB, the x component is a fraction of AB, same thing over here. Is that okay? All right, if you understand that, then I think you'll find the joint analysis pretty straightforward. Okay, so let's do this. Whoop. Let's do the method of joints today. Okay? Now, before we go down the rabbit hole, one thing I want to say is we are getting into a method where we're sort of surrendering our sign convention to a computer. Okay? And I want to be clear, that is something the structural engineers do all the time. So when they do that, they have to be consistent in their assumptions. So whenever you are doing that, or you generally don't know what to assume for a given result, what I would do is assume all members, hold on. To assume in tension. Okay? In other words, when I draw my joint analysis, I'm just going to put everything in tension. Now, why am I doing that? Well, if I do my math and I get a negative answer, it's compression, right? Just make a blanket assumption for everything right off the bat and just let the math do its thing, okay? And software programs do that all the time. So, better get used to it now. Okay, so we have member AB. We have member AC, which I'll sort of draw like that. We have a vertical load of 25 kips and a horizontal load to the left of 40 kips. And just so you know, I'm getting those are the reactions. So 40 kips to the left, 25 kips up. That's where I'm getting these. Okay. Again, assuming everything's in tension. Assume this is in tension. Assume this is in tension. Okay. Assume that's in tension too. So just assume everything's in tension. Let the math work itself out. Okay? Now this upper member is member AB. Okay? All right, so we'll call this ABY, ABX. Now ABY is 1 over root 2 AB. This is 1 over root 2 AB. This is ACY, ACX. This is ACY. And what do we have? 1 over root 5 AC. This is ACX, which is 2 over root 5 AC. Everybody see what I'm doing there? Okay. Now let's do each summation one by one. Okay? So let's sum forces in the X direction. Okay. So what do I have? I've got 40 to the left, and I have 1 over root 2 AB, 2 over root 5 AC going to the right. Oh. Okay. All right. So this is an equation. We'll call this equation 1. All right. I'm going to move this over a little bit. All right. Let's see if we can do the same thing for our summation of forces in the vertical direction. Okay? I'm going to scroll this up just a tad. Makes it a little easier for me to write. Do we have any forces going down? No, everything's going up. Whoop. All right, and as for what's going up, we have 1 over root 2 AB, 1 over root 5 AC, 25 kips. Okay?
Oh, you wrote 20.
25. Oh, you're right. Thank you. All right. I'm going to move this around a little bit so it's not so cluttered. You can't do this on a whiteboard, so I'm a little spoiled with this. Okay. All right. So we have 1 over root 2 AB plus 1 over root 5 AC plus 25 kips is 0. And then just so that it's in the same format, I'm going to take the 25 and move it over to the other side of the equation and say so that's going to make that negative 25. Okay? Is that okay? All right. So okay. All right, before I move on, does that make sense? Everybody okay with that? Okay. Okay, so everything from here on out is just calculator land, okay? So let's go through how to do that. Okay, so let's solve system of equations. Okay, so the way that we do that is we have two equations, and I'm going to sort of flip the order on this one, okay? So we have 1 over root 2 plus 2 over root 5 is 40, and then 1 over root 2 plus 1 over root 5 is minus 25. Okay? And then I'm then going to write that in matrix notation. So I'm going to get a table of values, which are the coefficients. The variables, and then the result at the end. By the way, your calculator does not know what you're terming X and what you're terming Y. So it is very important that you maintain an order. For example, in the first equation, I have AB first, then AC. AB first, then AC. So that when I plug this in, when it says X, that's AB. When it says Y, that's AC. So in calculator land, mode 5, 1. That's going to be your solution. Okay? So you're going to enter in this. Okay? And then you're going to get a X and Y term, and what are they?
For X, I got negative 127.28.
And for Y? And just press equals to get the Y.
145.34.
Is that, did everybody get that? No. Okay. So what that means is that AB is 127.28 kips in compression, and AC is 145.34 kips in tension. How did I get compression and tension? Negative, positive. I assumed everything was tension, so if I get a negative answer, just it's the other way. Okay. Does that make sense? All right. And again, if you have a calculator that's not a Casio, I have a playlist on Blackboard for several calculators on how to do this. So it should be pretty exhaustive. If your calculator's not on that list, tell me, because I'll find a video for it. All right. Sound good? Any questions on this? Okay. All right. Okay, I got one other thing I want to talk about today, and that is the identification of a zero-force member. In other words, we've been talking about truss members that either carry some amount of tension or some amount of compression. But it is possible that a tension or that a member in a truss carries nothing. No tension, no compression, it has no load at all. Okay? I always get this question. Dr. Mike, why would you put a member in a truss if it's not going to carry any load? Like, isn't the whole point that if you're doing, if you're building a truss, if you're going to spend money building a truss, that shouldn't the members be required to carry some force? Why would you have a truss member that carries no load? Okay, all right. There are two reasons why a truss member may have no force in it. Okay? One possible reason is that the truss member may not be intended to carry load. It may be intended to act as a bracing element for another member. Okay? Members in compression like to buckle, and elements framing into those compression members can act as braces. Okay? Bracing a compression member increases its capacity under buckling. So it may not be meant to carry load. It may just be meant to prevent buckling. That is one. Okay? A more practical reason for us is that they may be zero-force members if the loads do not move. Okay? So, for example, you have a truss, you have some loads on it, you analyze the truss. What if I move the loads? Maybe under load case 1, it's a zero-force member, but under load case 2, it's not, or vice versa. Okay? So it's possible that if, that's another reason why a member may be a zero-force member. So identifying them can be very, very advantageous. For example, see this truss right here? Bam, 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 bam. Zero-force members. Without doing any math, okay? You will be able to do this too. Without doing any math, I promise you all of these members, these internal members on this side of the truss carry no load. None of them do, okay? All right? And that's no math at all. And the way that you do that is there are 3 rules, okay? And if you follow these 3 rules, you can identify zero-force members relatively quickly. Okay. Rule number 1. Rule number 1 is if you have a situation where there is no load applied at the joint. Now, there's some caveats to this, but let me explain. So, if you have a joint that has two members with unknown internal forces, and there's no joints, or there's no loads at the joint, those 2 members are zero-force members. Okay? This is not necessarily true if you have a joint that has 4 or 5 members framing into it, but if you have a joint out in space that has 2 members framing into it, these 2 members, just these 2, no loads applied, these 2 are zero-force members. Okay? Now, that's not really magic, okay? That's just some method of joints analysis extended. Like, let's just ignore all the text, and let's just look at this free body diagram. I have a joint, I have 2 members, no loads. This is a diagonal, right? I'm going to take this diagonal, I'm going to split it up into X and Y components. How many unknowns do I have in the X direction? 2. How many unknowns do I have in the Y? So if I sum forces in the Y direction, what does that have to be? Because there's no vertical loads. So if this is 0, by the slope ratio, that's 0. And now, if I sum forces in the X direction, that has to be 0 too. Okay? So that's not magic. I mean, that's just me making conclusions using equations of statics. Now, this rule also holds true if you had a joint that had, let's say, 1, 2, 2, 3, 4 members framing into it, and you already figured out these two were zero force members. If that's the case, then these two are as well. Does everybody kind of understand this rule? Does this rule kind of make sense? Okay. Rule number 2. I call rule number 2 two members, and I call it collinear loads. Okay. So let's say you have a joint out in space. Two members framing into it. There's a load on that joint, but that load is in line with one of the members. Okay? I propose that the other member is a zero force member. Okay? And again, this just comes from statics. Let's take a look at this joint. Okay, here's a joint. I have a joint, I have two members framing into it, and I do have a load, but that load is parallel with this member. Okay, so what do? I split this up into X and Y, right? Some forces in the Y direction, that's 0. If that's 0, slope ratio tells me that's 0. What else does this rule tell me? That if this is 20 kips, that has to be 20 kips. That's how the statics works. Does that make sense? Okay. Now, a good example of where this happens is in situations like this. So if you have like a roller, and you have just like a 90-degree angle, whatever this reaction is, that member is carrying it, this is a zero force member. Okay. Does that make sense? Okay. Rule 3. Rule 3 is sort of the same thing as Rule 2. It's just if I have 3 members in a truss, 2 of them are collinear, and there's no loads, these 2 are the same, that's 0. Okay? And there's a lot going on with these rules, but I think the best way to digest these rules is with an example. Okay? So I'm going to show you an example here in a bit, and it's a pretty neat demonstration of the power of this process. Okay. Does everybody have all this? Okay, I see a couple people shaking their head no, so I'm going to give you a second. So yeah, but just to reiterate on this, if I have a joint out in space with no loads applied, but I got 3 members framing into it, if 2 of the members are in a line, they have equal forces and the other one's 0. But for this rule to work, there can't be any external loads applied. Okay? This has to be a joint out in space. And I mean, in a truss, not every joint experiences loads, so this isn't outside the realm of possibility. Okay. Everybody with me so far? All right. Let me go on to our example to sort of explain this. All right. So, I want to identify by observation the zero force members in this truss. Okay? And for the sake of discussion, we're going to assume that all the diagonal members are at a 1-to-1 slope ratio. So in other words, what that means is like this angle right here, that's a right angle. This is a right angle. This is a right angle. Because they're all at a 1-to-1 slope ratio. Okay? With me on that? Okay, now, in order to do this analysis, I find that the easiest way to go about it is to look at this a joint at a time and see if we can glean any understanding about the truss without really doing any equations or computations. What can we determine by observation? Now, before we go down the rabbit hole of zero force members, let's see what we can determine. This has a horizontal reaction, right? This has a horizontal and a vertical reaction, right? What's the vertical reaction?
50 kips up.
50 kips up. So that's just, I mean, that's not doing any math. That's just, you know, something we can figure out right now. Okay? Now, this is going to have a horizontal reaction. That's got to have a horizontal reaction that's equal and opposite, right? Because think, these two loads sort of act as the couple this way. So these two have got to act as the couple in the opposite direction. So we'll call this AX and GX. Now, we don't know what AX and GX are because we don't have any dimensions for the truss. We sort of need that in order to figure that out. I mean, we might be able to scale it and figure it out, but I'm just putting that out there, okay? All right. Now, I want to begin this assessment of zero force members by looking at this one joint at a time. Is there any joint that's particularly calling to anybody in the room that we ought to look at first? D? Okay, let's look at joint D. What's the deal with joint D? Joint D has no loads on it. It has two members out in space, and there's no loads. So what can you tell me about these two members? Zero. There's zero force members. That and that's a zero force member. So I'll just put 0, 0. That's a zero force member. Okay. So we looked at joint D. Any other joints you think we ought to look at? Let me ask you a question. Is there a conclusion that you can make about joint E? Let's think about joint E for a second. You're shaking your head yes, Mr. Collins. What are you thinking about with joint E?
E has to be 0.
This is 0, right? Because there's nothing going on horizontal. This is 0. By the way, what's member CE? And so is CE going to be experiencing tension or compression? Tension, right? Okay, so we're already figuring some stuff out. We haven't really done any math, okay? So this is a zero force member. This vertical one is not, but we know it's 50 kips in tension. I haven't even done any real math. Now, I propose that there are at least 2 more zero force members in this truss. 2 more. Somebody tell me another joint that we ought to look at?
H.
Okay, let's look at H. Why did you pick out H?
You've got 2 collinear members.
Yep.
1 extra off of it, that'll be zero force.
Exactly right. So, this is a zero force member. The other thing that I can tell you, and I don't know, I think I'm going to use like a square. These two members are going to have the same answer, right? So for example, if this member is 30 kips in compression, this one's going to be 30 kips in compression. If this one's 80 kips in tension, that one's going to be 80 kips in tension. So they're the same member essentially, right? Because think, if I removed this member, this is just a single, that's just a single element, right? So they're going to have the same answer. Okay? Any other joints we ought to look at?
C.
C. Okay, so what are we getting with C?
Well, there's kind of a collinear joint with BC and CD, and if CD is 0, wouldn't BC also
Well,
be 0?
that's true if both of these, well, keep in mind, okay, what about this, right? This has load. We don't know what this is. We don't necessarily know what this is. So I'm saying, here's the thing with joint C. Joint C has 3 members really framing into it. This one, and this one. We know this one carries load, and this one is not collinear with these. I bet these have some load in it. But there's another joint that we ought to look at.
G.
G, right? Okay, so why are you picking out joint G?
There's only,
What's that?
there's only 2 forces.
Okay, so we have this right here. There's 2 members. So this force is collinear with this one, right? So what's that say about this? It's a zero force member. See, think about it from a joint analysis. This has got to be 0. And what's going on with this member?
That'll be the same magnitude as GX in compression.
Exactly. It's whatever this value is in compression, right? Whatever the value is. I don't know what it is because we don't have any dimensions, but whatever it is. Interesting, isn't it? Look at how much of the truss we've solved without really doing any of the math. We found 1, 2, 3, 4, 5 zero force members. I know that this member is in tension, this member is in compression, and I know the magnitudes. It's pretty slick, isn't it? And we didn't do any math. I mean, we really didn't, you know. Really didn't do any type of computations. We just sort of looked at it. It's a powerful skill, and that skill will become increasingly relevant next week when we start looking at deflections. Okay? All right. Anybody have any questions? All right. You got a practice assignment on a 2x2 joint solution. You're only looking at a single joint, and I think it'll be faster. Hey, I have like a minute. We'll see if I can show you this real quick. So, hey, let me show you something. Just give me 1 second. All right, real quick. So, I'm going to do this real quick. I'll put this in the video so that you all have it. So, you can do these calculations in Excel as well. Right? And so this was, what, 40 and minus 25? Okay? I'm going to show you how you do this. This is really easy. Okay? So remember how we have to take the inverse of this matrix times this? Y'all remember that? Okay? So what I'm going to do is, over here, I'm going to type M inverse of this, press enter, and what it does is it generates that inverse. It'll fill all the cells. And then if you do what's called matrix multiplication of that and that, it gives you your answer. So you can do that in Excel if you want to. Don't worry, we'll do that a little bit later in Excel this semester too. So, you were 1 minute over. Counting me down. That's all I got, everybody. I will see you.